The E-MOSFET is somewhat similar to the D-MOSFET. They're both MOSFETs. They have that metal gate, the oxide layer, insulating layer, and then the semiconductor rest of the device. So in that regard, they obviously are in the same family and they're both MOSFETs. The big difference with the E-MOSFET is that no channel exists as it just sits there by itself. And you can see that here in the drawing, I think. The P substrate goes all the way across right against the oxide layer. This would be an N-channel example. So you can see the N-type that sits here and the N-type material that sits here. And there is no path. There is no channel from drain to source as it sits there. To get a channel to exist in an E-MOSFET, you have to apply voltage to the gate. And so that's the big difference. You can see that in the schematic symbol. You can see the openings here that are intended to show that no channel exists, as it sits there on its own. So the E-MOSFET gets its name because it can only be enhanced. The channel, the conduction can only be enhanced. It cannot be depleted from where it stands. It's already shut down and completely off. In contrast, the D-MOSFET can be depleted. If you remember the channel, there is a channel that exists, and it can be depleted or enhanced for the D-MOSFET. And here is our E-MOSFET N-channel with 0 volts applied to the gate. Again, you could just do that by shorting the gate to the source. And you can see no drain current is going to be able to flow. The channel is completely shut just as it sits there. For an N-channel E-MOSFET, you can apply positive voltage to the gate. And that is going to attract electrons, which are the majority carriers in the N-type. So it's going to attract them into the channel region. Maybe a simplistic way is you kind of think of it as pushing back the P region even. But the positive voltage at the gate is going to widen the channel. In fact, it's going to open the channel because no channel existed with 0 volts. And if you remember in the lab with the BS170 N-channel E-MOSFET that we used, it actually took a certain amount of voltage at the gate to even start creating a channel so that current could even start to flow. It was somewhere around maybe 1.5 to 2 volts, somewhere around there, in between there. And that voltage that starts to create a channel by pushing back that P region, that's known as the threshold voltage. If you remember VGS threshold, that's unique to E-MOSFETs. So yeah, it takes some amount to even get it going. So for an N-channel E-MOSFET, you would use positive gate voltage to control drain current. And again, it can only enhance or create the channel or widen the channel. There's no way to narrow the channel. At 0 volts shuts the channel down completely as it is. For a P-channel E-MOSFET, you would apply negative voltage to the gate to turn the device on. And I think you can see it gets a little tricky maybe to hold it all in your head. The transconductance curves, doing a quick sketch of those is the best way to straighten it all out if it starts getting confusing or mixed up in your head. For example, the N-channel E-MOSFET that we have here, you would apply a positive gate voltage to operate it. You would never do that to an N-channel JFET. You only use negative gate voltage with an N-channel JFET. With an N-channel D-MOSFET, you could put positive voltage to widen the channel. You could put negative voltage to narrow the channel. So you could do positive or negative voltage on a D-MOSFET N-channel. Only positive voltage on an N-channel E-MOSFET. Only negative voltage on an N-channel J-FET. And then everything switches. For a P-channel E-MOSFET, only use negative gate voltage. For a P-channel J-FET, only use positive voltage. I hope I'm saying this right. So you get the idea. I mean, to try to just rattle it off, you can get yourself tripped up sometimes. But that's what the transconductance curves are good for. Just sketch them out. That was that video I did that was a little fuzzy. I was shooting out on a glass white table. It didn't work out too well. But yeah, you can always just sketch them out to keep yourself straight. Of course, like we said, for a D-MOSFET, P-channel, N-channel, either one you can apply positive or negative voltage to. They'll have opposite effects, and so on. And just to wrap it up, with our N-channel E-MOSFET, we're using positive voltage to turn the device on, and you can see the current. It's going to run down through here. And if that was a P-channel, then the P-type would be here. The N-type, this would be N-type substrate here. Conventional current would run the other way like we did before. It would run this way. Of course, we'd have to flip this around. Whoa. That power supply would have to be flipped. And we would use negative voltage to turn it on, to open up a channel. And just to recap, if we go all the way back to a JFET, that's not what we have pictured here. I'll get to this. This is our E-MOSFET. But think back to the JFET, 0 volts at the gate. And for the JFET, the channel is as on as it can be. IDSS, and you can only deplete from that point. So JFETs are depletion-only devices. And then on the other end of the spectrum is the E-MOSFET with 0 volts at the gate. It's completely off. The channel does not exist. A channel does not exist. And then kind of in the middle, you have the D-MOSFET with 0 volts at the gate. A channel exists that can be widened or narrowed. So a good way to wrap all this up is to look at the transistor family tree. Altogether, well, you can see we have BJTs that we had studied previously, actual junction transistors. FETs, well, one of the FETs is a junction transistor, albeit we run it in reverse biased, but the JFET, you could argue, is a junction device. But we've got BJTs, FETs, field effect transistor. You know, what that's telling us is it's a voltage controlled device. It's a voltage field that is used to control that width of that channel, which is essentially controlling the drain current. If you remember the BJT, it was a small base current that controlled how much collector current could flow. There is sort of a hybrid device that kind of combines the two. An insulated gate BJT, or an IGBT, is really like an FET controlling a BJT, sort of. What you have is a gate and then a collector and an emitter. So there's places for those too. They're used a good bit. You can always look up sort of the two. FETs and IGBTs are both really useful in today's electronics for high power stuff. So those would be 3 broad categories. Now we can take the FET category and subdivide that into JFETs and MOSFETs. Like we said, the JFET is depletion only. It has a channel and it can only be narrowed. With MOSFETs, we can split that into D-MOSFETs and E-MOSFETs. D-MOSFETs have a channel that can be depleted or enhanced, narrowed or widened, and E-MOSFETs only can be widened. There's no channel that exists until you start applying some voltage.